Okay, this is hour 2 for Physics 1C for March 20. No, this is Physics 1A, section 1620 for March 31st. And we just talked about the work kinetic energy theorem, and I just wanted to mention something about this. Basically, what it states is that if you put work into a system, it's going to have the effect of increasing the kinetic energy of that system. So just as a really simple example of this, you have a box, and you apply a force on it. And if the box starts off with an initial velocity that we call 0, and you apply that force over some distance, delta x, so that the box ends up at some location like right here, what's going to happen to its velocity if you push on it? Is the velocity going to go up? Is it going to go down? It's obviously going to go up, right? So maybe the velocity at this point is like 10 meters per second. Why did the velocity increase? According to this, it would say you did work on the box, which had the effect of increasing its kinetic energy, right? You could have the reverse situation too. If I had a force that was pushing back this way, and the box started off with an initial velocity, let's say of 10 meters per second, okay, but we apply a force to the left, but the box still moves to the right, okay, this could be like you're pulling on a cord to slow it down or something like that, or you blow on it in this direction to make it stop moving, then you guys know that by the time it gets to this location here, it's going to have a different speed. Maybe its speed now is like 5 meters per second, right? So in this case, on the bottom, the work done is negative, which means the change in kinetic energy is also negative, right? The box slows down. And that's all that this statement says. It says that you do work on an object. If the work is positive, the velocity increases. If the work is negative, the velocity decreases. That's all it says. It's just a different way to analyze physical systems. It happens to be better than using Newton's second law to analyze systems because it can handle a wider variety of systems. Newton's second law can technically handle those systems too, but it usually leads to some very complicated calculus involving solving differential equations. And that's well beyond the scope of Physics 1A. And it's also something that if you can avoid it in any way, you try to do so. And we'll spend the rest of this showing how we can use this to solve problems. One in particular. We'll start off by solving, I think I moved them over to the right, didn't I? We're going to start by solving this problem here. Okay, so pop that problem in, and let's get to trying to solve it. So there's the problem. I'll give you some time to read it. You know, I could use these shapes, like this one in particular, to draw this picture. Yeah, it's not bad. So we have a system where you have a block here that's connected to a spring. Now I'm going to draw the spring a little bit differently. I'm just going to make the spring kind of this little jagged thing right here. But our box and spring start off in this position. It's a 4 kilogram block. We're going to call that M. So M is going to be equal to 4 kilograms. And it says that you have a spring constant K that's equal to 24 newtons per meter. That's the strength of our spring. And it says that the equilibrium position for our spring is somewhere over here. Okay, so this is x equal to 0. And our spring starts off compressing the spring by this amount, by 0.5 meters, right? And then it's released at rest. So we know that its initial velocity at this location, we're going to call this v sub 1, is going to be 0 meters per second. And we also know that its position, its initial position, and in the picture, I guess that position is measured relative to the edge. So we'll say this position right here, we'll call that x sub 1, and say that that's equal to, I'm going to say it's negative 0.5 meters. So I'm basically going to call this direction the positive x direction here. And it says it compresses the block by half a meter, and then it's released while at rest. Find the velocity when the spring is compressed by 0.3 meters. So what we're interested in doing is finding after the spring has decompressed a little bit, so that the box is now, let's say, like right about here. We're saying now that our position here, let me use a darker red. That pink is probably hard to see. Maybe this one. The position here now is going to be x2, and we'll call that equal to negative 0.3 meters. And I think what we're trying to find here is what is the velocity at this location. And let me just to save a little space. At this point in time, the box is obviously going to be moving in this direction with some speed. And that's what we want to calculate right here is what is that speed, right? It says find the velocity when the spring is compressed by 0.3 meters. A, if the surface is frictionless, B, if et cetera, right? So that first thing, that's what we want to do is we want to find what is that velocity V2 right there. Does the problem make sense to you guys? Does anyone have any questions? Okay. The first part we're doing is if the surface is frictionless. And that would imply that the only force that's really doing any work on this box is going to be the spring force, basically, right? The spring force which points this way. That's going to be the only thing that's doing any work on the box. So we're going to use our kinetic energy theorem, okay? And we're going to say that the work done by the spring should be equal to the change in kinetic energy of the object. The change in kinetic energy is going to be something like this. 1/2 the mass of the object multiplied by the velocity 2 squared minus velocity 1 squared. The work done by the spring, what's that going to be? Well, we got to go back a little ways. And we'll take this equation, we'll drag it down here. So that's the work done by the spring, and I'll make it a little bit smaller here. That's going to make it too junky. Like right around there is probably fine. That's what the work done by the spring is, right? So let's plug that in right there. Oh, whoops. I thought I had the eraser on. No, I need to do this with the pen, right? Oh, it's getting dark in my house. I need to turn the lights on. Give me 1 second. So that's the work done by the spring. That's what we derived earlier. And that should be equal to, yeah, everything on the left side here, right side here. So 1/2 m. But we just said V2 is what we're searching for, but V1 is 0, right? So let's just go ahead and say that term is 0. And then we just get 1/2 m V2 squared. And now it's just a matter of solving for V2 here. So there's a 1/2 on both sides. We can cancel that out. So we're going to get something like this. Negative k divided by m multiplied by x2 squared minus x1 squared. If I take the square root of all of that, that should be equal to V2. You can try to look at this, or you can just, the halves are going to cancel. You divide both sides by m, and then you take the square root because V2 is squared over here. And then we can plug in numbers. Before I do this, do you guys have any questions so far? So the spring constant is 24. Let's scroll down just a little bit here, so it's a little easier to write this. So 24 newtons per meter divided by m, which was 4 kilograms. X2 was negative 0.3, so this is going to be negative 0.3 meters minus negative 0.5 and that should give us our answer for what V2 is. Can you guys calculate that for me? Keep in mind that these negatives, use the mouse to point this out, these negatives here and here are inside of the square. So when you square a negative, right, you just get 0.3 times 0.3. Same thing as negative 0.3 times negative 0.3. The negative sign will get squared away. But that minus sign you do need to include. Oh, I left something out. Does anyone see what I left out? Going from this equation to this equation? Thank you. That's right. There you go. I used to hate it when I make mistakes, but now I love making mistakes because it gives an opportunity for you guys to show me that you're paying attention. So there we go. Go ahead and Why are the x values negative? Okay, the x values are negative, and they didn't have to be. But they're negative because I defined this direction. Oops. I defined the right to be positive. So the way I think about it is, here's our spring, right? It's like a number axis, right? Where this is 0, and this would be like x equal to plus 1. Oops, sorry. This could be like x equal to 0.5, but this over here then would be x equal to, as I said before, negative 0.5. That makes sense? Cool. All right, can you guys solve that and tell me what you get? What do you guys get? And I think if you round it up, it's like 0.98, right? Now, keep in mind that when you do stuff like this, right, we just square root. So there's actually two answers, right? In this case, I would say that the correct answer is the positive answer because it's moving to the right, right? Now, this is related to the question that was just asked in the chat. So Daniel asked, why are the x values negative? I don't know for sure, but I have a feeling, like if you picked your values in, you know, if you made the left direction positive, okay, I'm pretty sure that the calculation would have worked out to be exactly the same, except you would have had to choose the negative root. Does that make sense to you guys? Should I say that one more time? If I made positive x point left, yeah, I need to do this with the mouse so people on YouTube can see it. If I made the positive x point to the left instead of the right, this equation would have been different. The only real difference would be these signs right here. Like this sign would have been positive and this sign would have been positive. You guys following with what I'm saying right here? Make positive left. This would be positive, positive, and that's the only thing that would change. But guess what? You'd still get the same answer, except you'd have to choose the negative root. Do you guys see what I'm saying? You guys following along with what I'm saying here? It's so hard to tell without seeing your faces. It makes sense? Okay. So you need to keep this in mind when you're doing your homework. That's why I'm telling you this. There will always be, anytime you do a square root, you need to remember that there's a second solution to taking the square root. So keep that in mind. Don't blindly just follow the algebra. You need to use your brain at some point. So there we go. We found the velocity at point 2 was 0.98 meters per second. That's part A. All right, the next thing we want to do, let me get a different color pen here. So the next thing we want to do is part B. The only difference now is going to be if the coefficient of kinetic friction is 0.1. Okay. If the coefficient of kinetic friction is 0.1. So in that case, what's going to happen is what? What's going to be different now? If I need to add in friction somehow, how is that going to alter the original equation we started with here? How is that going to change? Definitely lowers the velocity for sure. Friction is going to absorb some of the energy. What else? What else is going to change about the equation here? The final answer will be lower. What do I need to do to change what I did here? The work from friction, but yeah, that's basically the idea. So now what I'm going to say is, if I take the work done by the spring, and I add to that the work done by the friction force, that should be equal to the change in kinetic energy for my system. All right? It's the same 2 points. The only difference is that now we have a friction force that acts, whoops, we have a friction force that acts back this way. And we can find what the value of the friction force is. Let me leave a little box right here too. Actually, let's do this. the size of the friction force, right, is equal to mu times the normal force. But in this case, because it's a flat surface, the normal force is just going to be equal to mass times gravity. So we've got all this information now. We just have to say, in our case, mu is equal to 0.1. So let's do that right here. So we have the work done by the spring, and this time I'll actually write it out. That was this expression here. The work done by the spring is negative 1/2 k x2 squared minus x1 squared plus the work done by friction is going to be equal to the size of the friction force, which is mu, times n. Oops, we're writing it as just mu times the mass times gravity. That's the size of, that's F, right? And we need to multiply that times the displacement, delta x. Okay? And I'm going to say in this case that delta x is going to be equal to x2 minus x1, right? x2 is equal to negative 0.3 meters minus x1, which is negative 0.5 meters. And this ends up being equal to then, I think 0.2 if you do that math, right? Negative, negative makes this positive. So this is going to be times delta x. I'm just going to label it as delta x in both cases, here and here. Somehow it connected there. I didn't need to make it do that. So delta x. But we need to multiply by one other thing. I should scroll up a little bit again. The displacement in this case is to the right. The friction force is to the left. So what's the angle between the displacement, which goes that way, that's delta x, right? And the friction force, which points to the left. What's the angle between the two of them? 180 degrees. Yep, so we multiply by cos 180, which is negative 1, exactly. And then the right-hand side stays the same. 1/2 mass delta k, 1/2 mass times v2 squared minus v1 squared. And that's the equation we need to solve now. That's negative 1. And which one's 0? v1 is 0, right? I need to scroll up a little bit so we can still see that. But v1 was 0 right here. So that's 0. Let's solve this equation now. We're isolating v2. I'm going to multiply both sides by 2 over m. The first term is going to become negative k over m minus, because of the minus sign, because of that minus sign, minus mu. Now, I left something out. We're multiplying by 2 over m, right? So if I multiply by 2, that shows up. But if I divide by m, it cancels with that m right there. So we're going to get 2 mu g times delta x. And that should all be equal to v2 squared, but we could also then just square root all of this stuff right here to get what v2 is. All right, does that make sense to everyone? Does anyone have any questions? All right, why don't you plug in for the values and see if you can solve it yourself. I'll do it on screen, but you know what k is, and you know what all these other things are too. So you go ahead and plug it in while I write the equation out on the screen. And tell me if you can get a solution for this. What is all of that equal to? Yeah, if you get an answer, you want to put it in the general chat, go for it. Is that what you got? I know it's 0.7 something. 0.775? This is... Did you not get something maybe like this? Yeah, okay. Yeah, you probably just typed a 7 twice by accident. Or just like... Here we go. And it's positive. It's less than this one, right? Which is good. We would expect it to be smaller, not bigger. You could have made a mistake here if you weren't careful, which would be probably at this location here. If you missed this negative sign, the fact that this becomes negative, if you miss that, then yeah. You can also think about it in the way that Ash mentioned, which is that you just need to subtract the work done by friction. However you want to think about it, friction is always going to reduce the amount of work done in the system. Okay. Do you guys have any questions? The last part of this question was, if the friction coefficient is 0.1, how far will the block slide? So how far will the block slide implies that when the block gets to this location right here, we're going to say the block becomes detached from the system. Originally it was touching the spring, but not connected, so the block is going to basically be pushed away from the spring at this time. So in that case, we kind of need a little bit of a new picture. So we start off with our block in one location, and then the block's going to end up here in another location. So we start off with the block compressed just as before. So it's compressed right here. And now what's going to happen is if this position is x equal to 0, and this was the initial x coordinate right here, where we said, I think x1 was negative, negative 0.5 meters. Now what's going to happen is that the spring is going to, so this is going to be x equal to 0 right here. The spring is now going to expand until it's all the way to here, but the block, which at one point in time would have been here, so the block at one point in time it was right here, it's now going to slide over to here, at which point it's going to come to rest. So now the block is here. And our goal is to figure out how far is it going to slide. Before it comes to rest. So we're also going to say here that for this block, we're going to say its final velocity, or v2, is going to be equal to 0. And again, we're saying mu is equal to 0.1 here. All right. Do you guys want to try this first before I solve it? It's a little bit different. I will identify that the block starts from rest, right? V1 was equal to 0. And we're going to go from this position all the way to this position here. The block is going to slide and come to rest at that location. And I want to mention one other thing here, which is I'm also going to say that the final x2, even though the block is at a different x coordinate, I'm going to say that this is also 0. And the reason why is because this x, in this case, represents the compression of the spring. And so if the spring is back to equilibrium, the equilibrium length, you might say, then x is no longer compressed here. That's why I say x2 is 0. So see if you can use this equation here to solve for the distance d that the object moves. Why don't you guys take like 5 minutes and try to do it yourself? Oh, hi. I'm sorry about that. I didn't have my mic on. I'll have to edit this out of the video later. So, here, let's just start over. Okay. So, did any of you guys get an answer yet for what D is? Anyone solve for it? That's okay. There wasn't that much time. So let's solve out what this would be. So the work done by the spring, right, was negative 1/2 k times x2 squared minus x1 squared. For the friction force, we found this was equal to basically the friction was mu times mg. And now we need to multiply by the total distance the object moves. What I was trying to say is that it moves a distance of 0.5 meters plus an additional distance that we call d. And the friction force acts that entire time. Can you guys tell me, what is the change in kinetic energy as it moves from this position all the way to this position here? What's the change in kinetic energy as it goes from here all the way to here? Anyone tell me? How much kinetic energy does it have at this location? Can you guys hear me okay? So what's the kinetic energy of the object to begin with? So want to answer in the chat? Anyone can answer? What is the kinetic energy of the block at position 1? Like, what's the kinetic energy right here? Yep, what's the kinetic energy over here? Yep, so what's the change in kinetic energy? Yep. Now we can write that down if we want to fully, but you know, if the velocity here is 0 and the velocity here is 0, then the change in kinetic energy is 0. Okay, so now we just have to solve for d. There's one other thing that we said was 0, which is this quantity here, x sub 2. We're saying that's 0 because the spring is no longer compressed in this situation. So this one is also 0. So what we're left with then is a pretty simple equation. We're going to have negative 1/2, right? Negative times negative is going to give us 1/2 k times x1 squared. And then I'm going to move this other piece, mu mg times. And then we can just solve this, right? We'll have k x1 squared divided by 2 mu mg. And then we'll need to subtract off the 0.5 meters. And that should be equal to the distance d. That d looks kind of funny. Can you guys calculate what that is? Not really much room here. So this is going to be so mu is 0.1, the mass is 4 kilograms, and g is 9.8. X1 was negative 0.5 minus. You guys calculate what that is for me? I'll bring this awful calculator up here and do it as well. So that's what I got. Basically 0.27. don't know if I made a mistake. That sounds... I thought I was going to get 0.25, but that's fine, I guess. 27 centimeters. Do you guys agree? Is that what you get if you calculate it? Cool. So that's to the right of the equilibrium position, which is about 0.77 meters total. Okay, so there's a problem. This took a lot of work to solve, but I think in reality, if you did this work on a paper, it wouldn't take you nearly as many lines. I'm just trying to show all the steps. Okay. All right, so does anyone have any questions about any of the parts of this problem that we just did? And if so, feel free to ask. All right. So the next topic then, it's going to lead us into the kind of final section of what we want to do here. We talked about kinetic energy. We talked about the work kinetic energy theorem. And the final thing we want to talk about are conservative and then NC, which stands for non-conservative forces. Am I cutting out a lot? Like just the internet, or is it not picking up my voice at some point?
I think it might be your internet, but like you cut out like mid-sentence, so it's a little hard to understand.
Mm-hmm. Yeah, so if I cut out mid-sentence, it's probably because of my internet. I am going to upgrade my internet to business internet connection today, which according to the internet company basically makes it so that I should get priority or something like that. It's quite a bit more expensive, but I'm utterly sick of dealing with paying the absolute most I can for residential internet and getting horrible quality, as you guys can tell. If I literally cannot pay any more for it. It's stupid. So then I talked to a friend of mine that I play games with, and he told me that he was having a similar issue and that he upgraded his thing to like Cox Business and it fixed the issues. So we're going to try that. Also, according to the tech... Go ahead.
If you listen to your YouTube video, though, the cutout shouldn't be there.
That's correct. Yes. It's all the recording is being done locally. So unless for some... No, I guarantee you, because the mic is open and it's picking up 100% of the noise that I'm making. So even if for some reason Discord doesn't pick it up, it's not getting transmitted out, it's definitely being recorded locally, and you can go back and watch the VODs. And I've watched the VODs, and I don't notice any of the, the breakup or anything like that, which kind of confirms that it is on the internet and not local, which is good to know, because otherwise I'd have to get a new PC, which I will, but it's, in this case, not necessary. I think I just need to... Apparently, I need to be a business in order to get good internet here in the city of Los Angeles, which blows my mind, but... It is what it is. There's very little competition for the major internet companies here. There's no one laying, or not enough people that are putting down like municipal fiber and stuff like that. But now I'm going off on a tangent. There's no point. Okay, so the last kind of topic for tonight then is conservative and non-conservative forces. So I'm just going to say NC for non-conservative forces. And we'll talk about non-conservative forces first. So a non-conservative force is a very simple definition. A non-conservative force is a force, the work done by the force depends on the path that you take. And I will give you a very simple example of this. Okay, very simple example. We take a surface, okay? This is going to be a tabletop. Not a tabletop, but a tabletop. On this tabletop, we're saying that gravity points into the board. So gravity... Oops. Okay, gravity's into the screen. And I mark off 3 points on here. Oh. So I mark off this point right here, which I call A. This point here, which I call B. And this point right here, which I call C. And I imagine 2 different paths that this object can travel along. One path will be this path right here. A straight line path going to be, we call path AC. Okay. The other path is going to be a path that takes us like this. Oh, and to be very clear here, we're moving an object on this table, okay? So I've got an object that starts off right here, okay? If we were in the classroom, I would use an eraser, and I'd say I'm going to move an eraser along the chalkboard from A to C, and then I'm going to move that same eraser along a different path from A to B, okay, and then up to C. Okay, so this is going to be just a box on a table, though, where gravity's pointing down, okay? And those are our two paths. So one path is going to be along AC, and the other path is going to be broken up into two pieces, but in general, we'll call that path ABC, okay? So you've got path AC, and you've got path ABC, like that. And what we're going to look at here is specifically the work done by friction. And we'll make a basic assumption that we usually do, that we say that the friction is a constant type of friction. No matter where you are in the table, the friction will always be the same, basically, okay? It's just like kinetic friction, basically, right? So I bet you anything you guys know the answer to this very quickly here. Along which path do you think friction is going to do more work? Path AC or path ABC? You can just answer in the chat. Is it along path ABC or path AC? I'm getting cut off again. Yeah. Yep. I'm sure I am. We're here at the peak hours when everybody's using the internet in my area, so we're getting bottlenecks. Yeah, that's right. That's right. Because it's a triangle and it's a longer path, right? So longer path leads to more work. That's easy, right? It's really simple to understand, I hope. If you had the option, like let's say that this was a floor in a warehouse and your job was to take some refrigerator box and move it between points A and C, unless there was some kind of blocking to move from A to C, you take the shortest path, right? You would do less work. Friction would take away less work if you moved along the shorter path, right? And so as a result, we say that friction is a non-conservative force because it's path dependent. So friction is a non-conservative force because it depends on the path that you take. The work done depends on the path you take. So we say it's a non-conservative force. If you take enough mathematics, you probably at some point in time, once you get to Calc 3, you start talking about vector fields, and you talk about conservative vector fields and non-conservative vector fields. Does that sound familiar to any of you guys? I don't know how many of you guys have taken Calc 3, but you will see this show up, and it's the same exact idea. So friction is a non-conservative force. Other examples of non-conservative forces could be, like I said in the problem, other examples could be things like a push force, the force of an engine, a drag force, okay? These are all what we call non-conservative forces because they depend on the path that you take. Every one of them depends on the path that you take in terms of how much work gets done by the force. That also implies how much work you need to do to overcome whatever that force happens to be, okay? That's a non-conservative force. Do you guys have any questions? Can you guys tell me any other examples of forces like this that you may have, like what's another force that might fit into this classification that you can think of? Is gravity going to work like this? What about a spring? So the spring, we've already basically proven that a spring doesn't fit into this, and I'll show you exactly why. It's because of this equation right here. Oops. It's because of that equation. Not that one. Let's look at the one that's... Here, this is fine. This equation... Why won't it let me do the select tool? Anyway, that equation right there. The work done only depends... It doesn't matter how you get between the points. The work only depends on x2 and x1, which is the endpoints of the path, right? Okay, so let's talk about that and let's prove that. Okay. So the next statement here would be to talk about what a conservative force is. So a conservative force is a force that the path does not matter, that the work done only depends on the endpoints. So we say the work done is path independent. The work done is path independent. And I'll prove how this works for a couple of these type of forces. Examples of these type of forces are gravity, big part of this class, springs, and one we don't talk about in this course, which is the electric force. These are conservative forces because the work done is path independent. The work done only depends on the endpoints. So let's give an example of this. Let's say that this is the ground, and I tell you that gravity is downwards, okay? The acceleration in the y direction in our system is going to be negative gj hat, okay? Just like the acceleration due to gravity on Earth, okay? And we say, suppose that I want to move an object now between 2 points, same thing. I want to move my object from point A up to point C, okay? And we'll have point B in here as well. And then we'll create our paths here. I think before the orange was the path color for the top one. So one path is going to go this way up to point C. I can just move this up a little bit here. And then that's going to be path 1. Oops. That's going to be path, we'll call it AC. And then my other path is going to be through B. So we're going to go straight to the right. And then we're going to go straight up. Okay. And that's going to obviously be, we'll call that one path A, B, C. They get to the same place through different places. The question now becomes, which one is going to take more work, or will the work done be the same? I'm going to call the length of the line AC to be D. So that length we're going to call D. And I'm going to define the angle down here to be theta. And I'm going to make that a right angle as well, in case it's unclear. This is a right angle here. So there's D, there's path ABC, and we need to think about what's going on with gravity in both of these scenarios here. So what I'm going to do is, oh, and this is some object we're moving, right? We're moving some object, like a ball, from here to here. And let's look at the forces that are acting on this ball. So the forces acting on this ball are going to be, there's going to be a force of gravity going down like this, right? And we're moving it, so there's some other force as well. But what we're interested in here is, what is the work done by gravity? That's what we want to find, work done by gravity. So in order to do this, we need to know something about the path the object travels along. What I would say is that it's traveling along a path that goes in that direction. And, you know, the vector associated with it, if we think about it, it makes an angle of theta here, and then an angle of 90 here. So I would say that along path AC, okay, so for path AC, the work done is going to be equal to, we can call this the work along AB. No, I want to call it the work done by gravity, actually. The work done by gravity is going to be equal to the size of the force, okay, that's mg, right? Multiplied by the distance the object moves, okay, that's d. And then we also need to multiply by the cosine of the angle between the two of them. Well, if the displacement vector goes this way, then that's the angle. which I would say is the cosine of, or the angle itself, is 90 plus theta. Does that make sense? I see a lot of people leaving the channel and rejoining the channel. Is that so you can like close and reopen the stream? Is that what's going on? I apologize if there's like any lack of quality. I wonder if I'd closed the stream and reopened it, if it would have, why is it 90 plus theta? Oh, okay. Well, the object is traveling along a line like this. The gravity goes down like this. That angle at the bottom is theta, and this one's 90. So you have to do 90 plus theta. Does that make sense, Shrek? Okay. Why doesn't it want to pick that one? I just want you to pick. There it goes. Nope. It's not doing it. Okay, we'll just not worry about it then, I guess, or something. Click. Am I doing something wrong here? No. Can I select any? I can select this one. So maybe I gotta go here and then here again. And then here. Okay, we're just gonna not worry about that right now. Keep going, if I can. Get my pin back. It's not happening. Got this different kind of looking thing here. What if I go here and then here? It's almost like it's forcing me to select this. Let's see if I just select something and then delete it. Is it now going to let me do something else? It did. Okay. All right, so work done by gravity along this path was mgd cosine 90 plus theta, right? All right, let's look at path ABC. So along this path, there's kind of two motions, okay? The first motion, you're traveling at a vector that goes this way, but the gravity force is down like this. So the angle between the two of them, if I wanted to find, for example, the work done along AB, let's use green for this. We'll come back to this line. The work done by along section AB. Now, it's still the work done by gravity, so I need to be more clear about this. I'm going to say along AB, the work done by gravity is going to be equal to mg multiplied by the distance between these 2 points. And here I would say that that distance is going to be, here, let's erase this real quick. The distance from here to there is going to be d cos theta. And we can say the same thing over here, that this distance is d sine theta. So we would say the work done by gravity along segment AB is mg times d cos theta, and now my color's changed again, I didn't mean to do that. D times cos theta. But then we also need to multiply by the cosine of the angle between the path vector, which is this way, and mg, which is down. So we also have to multiply by the cosine of 90. So this is going to be 0, because cos 90 is 0. Along segment BC, the work done by gravity is going to be equal to the weight of the object. Now I need to draw another picture here. So now the weight in this case goes down, so that's mg. And the displacement vector is this way, call it delta r or something. So the angle between these two, right, is 180 degrees, right? So now I would say the work done by gravity in this case is going to be mg times the distance it travels, which is d sine theta. Okay, that's this piece. Multiplied by the cosine of the angle between mg and delta r, which in this case is 180 degrees. So this is going to give us the work done by gravity is cosine 180 is negative, so you get negative mgd times the sine of theta. That's the work done by gravity, and this is for the path ABC. Negative mgd sine theta, right? Okay. the thing is, if we come back to this expression right here, there's a relationship that we can use from trigonometry, which tells us that the cosine of 90 plus theta is equal to, maybe you guys know what this is, it's equal to the negative sine of theta. Which means that the work done by gravity here also is equal to negative mgd times the sine of theta. So you get the same answer here and here. The path doesn't matter. You get the same answer regardless of what you do. Does that make sense to you guys? Does anyone have any questions? That's why we say that for a conservative force, that the path is independent of for the work done. The work done is independent of the path chosen. All that matters is the endpoints. That's it. The only thing that matters is the endpoints. So do you guys have any questions? Okay. So there's one other topic that I want to talk to you guys about, and that's like the length of the limit of what we're going to do tonight. There's another problem I want to do. We need to take a break. All right, we're going to take an 8-minute break, and we're going to start again at 8:10. So I'm going to stop recording.